Welcome back, and yeah, just let me know once you're done so that I can start. Oh, how was my weekend? Thank you. Just give it over. That's what you should do. Thank you. It was a relaxing weekend. Thank you. So let's see, where we are is very important part of chapter 4. We are working on applications of derivatives. So far, we have talked about related rates and absolute max mean and critical points. Today, the plan is to make sure that we have enough tools to identify local max min. Local max min is a bit different story than what we had for absolute max min. And here, the main tool we would use is the first derivative. And today's basically lecture, I should write, is the first derivative test. It's in other words, how we can use first derivative to say or to identify some information about the function. In particular, how to find or identify which one of the critical points are local max or local min. Okay? Let me recall this thing, that what is increasing function, decreasing function. So let f be a function defined on, here I just need to have an open interval. Doesn't matter. The endpoints is not important. So we say f is increasing function if, as we go to the right on the x-axis, the values of the function goes higher. If I want to write that mathematically, is this. If the value x1 is less than x2, then f at x1 needs to less than equal to f at x2. This is the definition we would use, and it will work properly for our lecture. Well, accordingly, accordingly, I can define decreasing functions, which is as we move to the left, to the right, the values of the function gets smaller and smaller. We want to develop or find a tool which tells us when a function is increasing and when a function is decreasing. Or in other words, I am looking for a tool that can help me to identify increasing interval and decreasing interval or walls of a given function. The key point here is observation. When you have a function which is increasing, I have to be a little bit careful, so I'm putting some details under the rug here. But just say that here is my function, which is increasing function. Then if I have at any point, if I sketch the tangent line to that function, the tangent line also going to be increasing. In other words, increasing function on an interval with a bit of not mathematically correctness implies that slopes of tangent lines are bigger than equal to 0 as well. So if my function is mathematically correct, would be strictly increasing, then my slope of tangent lines would be also like that. It means that at any point, f prime also going to be bigger than equal to 0. So that is the important fact that if you want to make it mathematically correct, you need something called a version of mean value theorem, which we won't cover in this course. But that is where this whole idea comes from, and I want to write that one. So I write first derivative test, or first derivative, and increasing, decreasing intervals. Mathematics of this intuition comes with this. Let f be differentiable on a given interval. Then we have if f prime of x is bigger than or equal to 0, if it is non-negative for all x in AB, then f is an increasing function on the interval AB. If f prime is bigger than or equal to 0, the function is increasing. If f prime of x is less than or equal to 0 for all x in AB, then f is a decreasing function on the interval AB. Function. And well, this is not part of it, but it is important to know that if f prime of x is 0 for all x in AB, then f is constant function. I think there's a good reason to put all three in one place, because if you know mean value theorem, these are all result of mean value theorem. What does it have for us? This is the tool we are looking for. This says to determine where the function is increasing or decreasing, you completely forget about the function itself and go to its derivative. Find the sign table of f prime. If f prime is positive on an interval, the function will increase. If f prime is negative, the function will decrease. Let us do some examples, and then we'll get back to this. Any questions, any comments so far? Straightforward. Examples, find increasing, decreasing intervals of the given functions. The first function I have is a simple polynomial. It's 2x cubed minus 3x squared minus 12x plus 5. Find increasing, decreasing interval of this function. Okay, I'll do this one myself. As always, I pick the easy examples myself. I do it myself, but the more difficult ones are for you. Okay? I just want to show how this works. I want to find increasing, decreasing interval of f. For that, I want to find the sign table, or where f prime is positive, where it is negative. So I need to find what is f prime. Now, to find the sign table for f prime, I always, or in general, I always start with where this function is 0. So I want to find the sign table of this. I want to see where it is 0 first. So set f prime equal to 0. This implies 6x squared minus 6x minus 12 is equal to 0. Factor, let's do this, 6 x squared minus x minus 2. This must be equal to 0. And, well, factoring of this is easy. This is just two numbers adding up to -1 and multiplying to -2. That's 1 and -2, yes? And that being 0 means either x is 2 or x is -1. F prime, which is a quadratic function, has those two roots, and I can just go ahead and say, okay, now, this was what I was trying to find. The sign table for f prime x. I know that at -1 and 2, at -1 and at 2, my function is 0. Then these are the only zeros using intermediate value theorem. Then this part, this part, this part will have only one sign. And to find that sign, I just need to plug in some values. For example, if I plug in x equal to 0 into f prime, we get -12. So that is how you get that interval, whole interval negative. You do the same game or any similar. I am not really asking you to do exactly the same thing. Find the sign table, whatever works for you. But remember, we are finding sign table for f prime. And what does it have to say about f? We know that f prime positive means f is increasing. F prime negative means it is decreasing. So increasing intervals, there are two of them, -infinity to -1, and there is 2 to +infinity. Decreasing interval would be from -1 to 2. That's how we show, or how we use this theorem to identify increasing, decreasing intervals of the function. You should really appreciate what does this theorem do. Without this tool, identifying where this is increasing, decreasing is a hell of a work. It's a painful work. I'm not even sure you can, one person in this class, even including myself, can do it in a acceptable time frame without using that fact. It would require millions of steps to identify where this is increasing, where it is decreasing. Yes, please.
You know it was plus, negative, plus. Like, what do you plug in to find that?
Sorry, how did I know where? Where are these ones? Okay, remember intermediate value theorem? If a function is somewhere plus, somewhere minus, between them there should be some zeros, yes? If I ignore all the zeros, that means that everything here should have only one sign. Because if it was at some point plus, some point minus, yeah, then it had to cross. There would be some zeros over here. Okay, when they're done, I will explain the rest. Okay, so I just need to pick one value. For example, here, pick x equal to 3. Plug in into this, 9 minus 3, 6 minus 2, 4. It's a positive number. Everything in this interval will give you positive value for f prime. Pick a number here, x equal to 0. Put into that. It's negative 2. It's going to be negative, and so on. Yes? There are other ways also to do this. I don't want you to only do this one, but whatever works the best for you, there are more than one ways to do it. Any other questions, any other comments? Why don't you then try to do the same example, like increasing, decreasing function. For this interesting and nice function. I'll give you 90 seconds. And I expect you to be able to mimic steps like this with the plan that I'm going to use the first derivative test or first derivative for increasing, decreasing test that is written on the board. 90 seconds starts now. Go ahead, please.
They give you 0.75. They give you. I just logged into it all. I'm open. That's what I was accounting for. I was accounting for.
To find increasing, decreasing interval of a function, we find the sign table for its derivative. Here, then I need to find the derivative of this function, derivative of numerator. times the denominator minus derivative of the denominator times numerator over the denominator square.
Okay.
And here we get 2x to the power 5 minus 4x to the power 5. So that gives me this, and then plus 2x. 2x times 1. Yeah. One thing here to note is that the derivative, even though it has the denominator, but denominator cannot be 0 because x to the power 4 is always a positive number. You add 1 to that, it cannot touch x-axis. So note, not only the denominator cannot be 0, but also it is a number always strictly bigger than 0. Why is it important? Because when I'm trying to find the sign of g prime, the denominator is always positive. Positive denominator is not going to play any role in the sign of your function. So in other words, you just need to be worried about the numerator. G prime equal to 0 implies this is equal to 0. And let me just factor this, negative 2x, x4, then minus 1 is equal to 0. Either x is equal to 0, or x to the power 4 minus 1 is equal to 0. So then you get two values over there, and one of them, which is x squared equal to 1, will give you these two. The other one, which is x squared equal to negative 1, doesn't have any real roots. Okay, now I have everything for g prime. X, negative infinity, negative 1, 0, 1, plus infinity. These are where g prime is 0. And that implies that, then each interval will have only one sign. I just need to look at this one, the numerator, and evaluate it at some points. For example, if you plug in x equal to 2, then you get a negative number. Then if you plug in, for example, 1 over 2, you get a positive number. In this case, everything will work nicely, and you alternate at each point. Result of that is sign table of g prime gives us increasing, decreasing interval of g. And we have two increasing intervals, two decreasing intervals. So increasing intervals are negative infinity to negative 1, and from 0 to 1. Decreasing interval are negative 1, 0, and 1 to plus infinity. We will do some more examples, but let me just stop here from the example side of the story, and then we go to the first derivative test. Is there any questions, any comments before we move to the next topic? Okay. A small recalling point here is that remember that we had a theorem, Fermat's theorem. You remember? It said if a function has a local max or local mean at a point, that function at that point will either have no derivative, or that it's not differentiable, or its derivative is going to be equal to 0. We call those ones critical points. So recall that Fermat's theorem said local max and min happen only at critical points. So if you are looking for local max or local min, the first thing you should do, find critical points. Fermat's theorem, what it doesn't tell us is that which critical point is local max, or which one is local min. The only thing Fermat says is that, well, you're looking for local max min. It should happen in one of these points, critical points. We want to find a tool that goes then to the next step and says, okay, if it is critical point, when it is going to give you local max, when it is going to give you local min, and when it's not going to be a local max min. This is called the first derivative test. Says let C be a critical point for f, and f is continuous at C. In other words, the function is not differentiable at C, or it is differentiable and it is equal to 0. But I want to make sure that my function is continuous at that point. Then there are 3 cases, but easy way of remembering this is this, that only critical points at which f prime changes the sign is going to give us local max and min. If f prime doesn't change the sign when we cross that point, it's not going to be local max min. Or in more details, if f prime instead of writing that, let me do this. If f prime around C first is plus, then negative, in other words, f prime changes sign from plus to minus at C, then f has a local max at C. So if it is plus before C and then becomes negative after C, that will give us a local max. If f prime around C is first, before C is negative, then it becomes positive. In other words, f prime changes from negative to positive at C, then f has a local min at C. The third part is that if f prime doesn't change sign, if it was plus, stays plus, if it is minus, stays minus, then f doesn't have any local max min at that point. If f prime does not change sign at C, then f does not have local max nor mean at C. How should I remember all these rules? Based on the fact that plus f prime being positive means increasing, you just can play with f itself and see that. This means f first is increasing, then decreasing. So you're dealing with something like that, and that gives you local max. If it is first decreasing, then increasing, then you're dealing with local min. That's how you should remember. What about the example? Can anyone come up with an example where C is a critical point, but f prime doesn't change the sign at C? Yes? Isn't that saddle point? Do you call it saddle point, those points? Like, what is the example of that? X cube, okay, yes. So that in x cube, the function is increasing before 0. At 0, it gives you a critical point, and then again, it continues to be increasing. Yes. Was there any question, any comments back there? Then let's look at these functions here. Now someone can ask you, find local max mean of the given functions. Here, in this case, I have a cubic polynomial. It means it's everywhere differentiable. The only possibility for critical points is when f prime is equal to 0. So we have two critical points. And then I want to use the first derivative test. At 0, before 0 it is plus, after it is negative. So function first increases, then decreases. So here we have local max. At 2, it first decreases, then increases. So this is local min. So the function has one local max, one local min. In this case, again, function is continuous, differentiable everywhere. We differentiate, set it equal to 0. We have critical points, and then when we look at the sign table at those close to those points, we have first plus, then minus around -1. This is local max. At 0, it is local min. At 1 is local max again. Let's do one more example here. This is find local max min of the function, let's call hx, is equal to, what is hx? X e to the power x squared minus 3x. find all points at which the function hx, which is x times e to the power x squared minus 3x, have either local max or local min. Go ahead, I give you 90 seconds. You try from finding critical points. Try to use the first derivative test, means that you have to set up the sign table for f prime, and then use the first derivative test to identify local max, local min. Go ahead, please, 90 seconds. I'm expecting you at least to be able to find all the critical points of this function. H prime needs product rule. Derivative of first one, e to the power x squared minus 3x, plus first derivative, the first one times the derivative of second one. Remember, the derivative of e to the power u is u prime e to the power u, yes? So in this case, u prime is 2x minus 3 times e to the power x squared minus 3x. Okay, remember that we want to find the sign table for f prime. So I need to simplify a little bit. And in this case, it's not very bad because e to the power x squared minus 3x is factors of both terms. And we can write like that. And then here we have 1 plus 2. OK, let me write maybe from that. 2x squared minus 3x, then plus 1. OK? That's h prime. That's the derivative. We set it equal to 0. One thing here to note is this important point, that e to the power any real number, remember the graph of exponential function? It never touches x-axis. It means that no matter what I put here as real number, e to the power this cannot be 0. The only factor can make this h prime 0 is this factor. In other words, we have to solve this piece here. How should I solve that function, that equation now? How should I solve that equation? Did anyone solve it?
Plus 1.
Isn't this plus 1? Sorry, yes, please. Well, we can try to factor it. Remember, it's not very difficult factoring when you have a coefficient here. It's not very difficult. But can't we use just quadratic formula? Quadratic formula is there for us to use, yes? So I can go x must be minus b plus minus b squared minus 4ac over 2a. This is 3 plus 1. 9 minus 8 is 1 divided by 4. So what we found are critical points, which are, if I put plus, this is 4 over 4. And if I put minus, it's 2 over 4, which is 1 over 2. I found critical points. Function is everywhere continuous, everywhere differentiable. Yes, please. No, I can factor it. The only thing tricky part is there's a 2 here. You have to be careful on that, yes? I felt if I use quadratic formula, it will be less painful. That's why I used that.
Quadratic formula one.
Well, more complicated. I would say, remember, just one thing. Quadratic formula always works, but factoring sometimes can get tricky. Yes? Just keep that in mind. I'm okay with the rest. Now, I have critical points. I want to use the first derivative test. So we want to find the sign table. We want to find sign table for h prime. Again, remember, e to the power real number is always positive. So the only sign that is going to h prime have comes from this part, and that is plus, minus, plus, or do whatever works for you the best, yeah? And then this means that, see, at half, before it is increasing, then decreasing. So x equal to half gives local max. X equal to 1 gives, before x equal to 1 is negative, after it is positive. If you want to keep everything a bit more organized, I would say still figure out where the function h itself is increasing, where it is decreasing, and that will clear out everything for us. Any questions, any comments? You good? Yes? So these calculations are the same. Basically, any example I give you, you should be able to go through the same things. Well, each one may have its own tricky game, but at the end, the steps are completely the same thing. I think we have enough time to do one more example. I love this example because, okay, I'll do this one. Example. F is differentiable on the whole real line, and the graph of f prime is given. Find local maximum and increasing, decreasing intervals for f itself, not f prime, f itself. What is the graph of f prime? It goes like this. Here is -2, -1, 1, and 2. Remember, this is the graph of f prime. I will give you 45 seconds. I'm not expecting you I'm not asking you to solve it. I want you to talk to the person sitting next to you and try to go through these three things. If this is f prime, what are critical points where the function f is increasing, and what are the points at which we have local max, local mean for the function f? 45 seconds, I want you to focus and talk with your friend on these things. And remember, the graph is for f prime. Go ahead, please. I want to hear a bit more chatting.
Yeah, go to negative.
10 more seconds. Wrap it up, wrap it up. Can anyone tell me how many critical points we have? Yes. 5. Oh, I see. That was the answer. 5. And here, just note, this is f prime. When you have f prime, critical points are the ones that make f prime 0. Remember, this function is everywhere differentiable, so we don't have the other type of critical points. And it means, okay, I have 1, 2, 3, 4, 5 points at which f prime intercepts with the x-axis. So critical points are -2, -1, 0, 1, and 2. Now, increasing, decreasing intervals, we have f prime, and we go -2, -1, 0, 1, 2, plus infinity. Here, what I'm interested in knowing is that where f prime is positive. In other words, where the graph of f prime is above x-axis. And this shows if we have from -infinity to -2, if we are between -1 all the way to 1, and then from 2 to infinity. And f prime being negative means where the graph of the function f prime is under the x-axis. -2 to -1 from 1 to 2. And there we go. We have increasing, decreasing intervals because here is positive. So this increases, 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 decreases, decreases. Now, local max, local min. At -2, the sign of f prime changes from plus to minus. So this is local max. Here is local min. At 0, f prime doesn't change the sign. So it is neither local max nor local min. Here is local max. Here is local min. Have a great day. Next class is already in. Hello.